the quality of our services and the content that's delivered from them. And one of the projects in this track is on predicting how long queries in our information retrieval system take, or how much resources they consume. And a particular uh, interesting part of this, or challenging part of this problem, is the fact that the data we work with is very, very noisy. Meltwater are one of the world leaders in media intelligence. Our customers use our platform to perform search and analytics on online media to find out what's being written about themselves, about their customer or their competitors, their industry. They want to know who's writing about them, what's being written about them, is it positive or negative. They want to monitor influential conversations, trending conversations, find out the social impact and political impact of different campaigns that they're running. They want to monitor their brand to see how it's being perceived in online media and have all this information presented to them in a very concise and easy to understand way. And all this is backboned by a 500 plus node Elasticsearch cluster. And this cluster is managed by the information retrieval team, of which I'm part of, which is an 8-person team based here in Gothenburg. We're known as Team Horace, named after the orangutan Horace, was the librarian of the Unseen University in the Terry Pratchett Discworld novels. And like the orangutan Horace, we're also the guardians of a huge amount of documents. We've over 35 billion documents in our cluster. These are taken from online news sites, other online publications, blogs, Twitter, other social media, and it's increasing by about 75 million every day. And if somebody wants to search in this document store, there's a variety of different user interfaces, but it reaches our subsystem in the form of a query that's specified in a JSON, formatted JSON. So for example, if I want to search for information about this conference in online media, I might create a query that looks for documents matching all of the terms GAIA and conference and one of Gothenburg or Göteborg, and maybe excluding the term Greek to avoid confusion with the Greek goddess of the same name. And we get over 2 million searches every day. And typically we can respond to them within 1-200 milliseconds, so which is fairly good for something of this scale. But not all queries are this simple. Just take a couple of examples from queries we've received this year. On the left, this snippet is using wildcards, and it's searching for documents matching A star, B star, C star, D star, and you can guess what the rest is. So it'll hit pretty much every document in our cluster. On the right, we have another snippet. This one, if it was expanded, it expands to 223,349 lines of JSON. And this is actually a valid query, this one, or a valid use case. It's a generated query that combines lots of smaller queries to create a newsfeed for a customer. And it takes, when it ran in production, it took about 86 seconds, which is not too bad for a query of this size. But the problem is not this query itself and how long it takes to run, but the problem is the effect it has on queries that are running concurrently with it. Because what we can see is that we have these large spikes in the average search time. So these big difficult queries come in, they use up lots of resources, they create queuing in different parts of the system, and the average search time raises to seconds or minutes instead of milliseconds. So this is a problem, this is what we want to try and solve. So the first step we took is we created a search router, and we split our cluster into high priority, or low priority, and normal priority queries. And we know that some of our queries are non-interactive. They're coming from reports, weekly reports, or other types of reports. There's not a user sitting at the other end. And for those, it doesn't matter too much if they take some time. So those we can route into the low priority part of the cluster. But we also have interactive users who are actually sitting at the computer, typing in queries and expecting responses within seconds. These we don't want to be taking minutes. These are the users that this really negatively affects. So those queries we can send to the normal priority zone, and this has helped quite a bit. But interactive users can be really creative in the queries they write. They can manage to write some very complex queries, and we still see a lot of search spikes. So the next step we want to take is we want to be able to predict how much resources a query will use before we execute it. And if it's going to be a heavy query, if it's going to use a lot of resources, then we want to push it onto the low priority cluster so that we know it's already going to take a lot of time. It's okay if it takes a bit longer, but we don't want it disrupting all the other queries. And to do this, we have a large history of log files of previous queries that have run. We can train a model on using these existing queries, and this model then can be used in a resource prediction service to provide predictions on how long or how much resources the queries will actually use. And our search router can then use this information to make smarter routing decisions and to try and restrict the queries that are going to the normal priority zone to be those that we think are going to be quick to execute. Elasticsearch in 30 seconds. Documents, when they enter Elasticsearch, are assigned to an index, which is a logical namespace, and that index corresponds to one or more physical shards, which are containers of the documents, and the shards also contain the worker processes that can search through these documents. If we want to estimate a resource consumption, we can take the query time, so how long the query took to execute, and multiply it by the number of shards that that query hit. So if a query just hits a single shard, it's probably not as it's not using as much resources if it's hitting multiple shards. And the query time, we can measure the number of shards we can derive just based on the query and our knowledge of how we've set up our cluster. So this is what we're trying to predict, the resource consumption. And we have, like I said, we have lots of logs. We have a history of all the queries that have been executed in the system, and we can extract features describing those queries. And we have this measured resource consumption that we've seen when the query has executed. But the problem is that this is very noisy, because the queries execute in parallel, sometimes hundreds of queries in parallel, and they're all competing for the same computing resources. They're all passing through the same queues. We can't fully trust this measured value. And just to take 4 completely random queries, so each marker here is a different query, and I've executed it 10 times. And the variance or the standard deviation of each query is quite large. So if I run it now and if I run it in 5 minutes, I might get a completely different measurement. So this is a problem. But let's say we ignore that problem for now, and we try to build a model. So we have a number of features that we input into the model. The features describe the characteristics of the query, and we train it using this measured resource consumption, which we know to be noisy. We're using Keras on top of TensorFlow, which is very flexible, so we can have inputs and an output and configure the topology whatever way we want to. We'll call this our dynamic noisy model. Noisy because it's trained on the noisy data. Dynamic and online because it can just take a flow of logs and train in an online manner, and it can be continuously updated because we can just keep feeding the logs into it, and that way it can actually adapt when the cluster changes, as more documents are added to it, as the hardware changes. Even if we do software updates, the model will keep learning, so it's dynamic. But the problem is how do we validate this? We know the measurements are noisy. So how do we know if it actually works? Well, one thing we can do is, luckily we have a staging environment, which is a scaled down version of our production environment. And there, in our staging environment, we can run the queries, we can replay the queries one by one. And we can do it multiple times as well to get a kind of an average and a more stable value for that query. So that will give us a clean measurement. And this means that we can validate our dynamic noisy model against these clean measurements. And we can even do, but why stop there? We can actually also maybe build a model using these clean measurements. So why use the noisy measurements to train the model? We can just use the clean measurements. One problem with this is that this model is then static. Because it works using, or it's trained using these clean measurements that are only obtained from our running queries one by one in our staging environment, we can't do it online for new data that's coming into the system. So it's using a better measurement, the clean measurement, but it's static, it can't evolve. Another problem is that it takes a lot of time to gather these clean measurements, because running them one by one multiple times is a lot slower than running hundreds in parallel. So just to give an example, to get about a half a day of clean measurements takes roughly a week in our system. So this is a limitation. It creates a limitation on the data sizes. And another limitation is that there's other people using the staging environment, other teams, and may not be so happy if we disrupt their service by performing our experiments. So can we do better than this? Well, what if we could estimate that clean metric instead? Or what if we could take the noisy measurement and get rid of that noise? If we could denoise the noisy data to get an estimate of the clean data. So that's what we're going to try to do in our third strategy here. So now we create a new model, and in this model one of the inputs is the noisy measurements. So up here, if I can control the mouse, here we have the noisy measurement as an input to the model, and then the clean measurement as the output. So this model then becomes a function that transforms the noisy measurement to a clean measurement. And the parameters of the function that will allow us to do this transformation are the features of the query, but also the features of the context of that query. And in this case, the context is the queries that are running concurrently. Because from our log files, we know what queries have been running at the same time. So then we're able to get features from those and use this in our denoising model, because we know that those are the queries that are causing the noise. So then we have a model that will denoise our noisy data. But that on its own is not going to help us solve our original problem, because it takes as an input the noisy measurement. And this is, yeah, sure.
What kind of metrics do you use for the aggregate queries, the other queries running in the same context? Is it again the features of those queries and the time they are taking? Or
it's the features of the queries. It's not the time that they take themselves, because that in itself might be noisy, but it's just it's actually the same features except aggregated, but on those other queries. But yeah, this on its own is not good enough, because we can't. This is just a model to denoise the noisy data. We can't use it to predict queries coming into the system, because one of the inputs is the noisy measurement, which doesn't exist when the query comes into the system, and also the context doesn't exist, or is not easily obtained. So we also need a second model that then actually trains on this denoised measure. And the denoiser model, that is static. That must be trained offline because it's dependency on the clean metric. But then this denoised model, that can be dynamic. So this can actually process a stream of queries that are coming into the system and first denoise the noisy measurements and then train a model to predict new queries coming into the system. So this is our dynamical denoised model. To compare these different approaches, we'll look at the validation error. And not too surprisingly, the clean model, the model that actually trains on the clean measurements, is what performs the best. And now we're also validating against the clean measurements, so it makes sense that this is what shows the best results. And the dynamic noisy model is over four times worse when it comes to validation error. But the denoised model is fairly competitive, even though it's using the denoised metrics or measurements. And it's only 8% worse. And this comparison is done using a fixed training data size. So the static clean model has used the same data sets as the dynamic denoise model. But as I mentioned earlier, the clean model, that's very restricted in how much information it can train on, because it takes so long to collect those clean measurements. Whereas the denoise model, while the denoiser has the same restrictions as the clean model, actually, once we have a denoiser, we can then run it through as many requests as we can handle. So this can handle we can get much more training data for the denoise model. So if we then try increasing the training data set for the denoise model, we can see that it will actually be the best model in this case. So when the two models use the same training data size, so this is the leftmost bar here, we see that 8% different, that the static model is better. But already once we've reached twice the data size, the dynamic denoise model produces better predictions. If we increase it up to 8 times the training data size, we get over 20% improvement. And this is, it's given how slow it is to get clean measurements, getting 8 times as much data for the denoised model is actually quite easy. It's only a matter of hours. So this is a nice result. And it means that the best strategy that we have for this problem has been to use this dynamic denoised model. But back to our original use case, can we improve our routing decisions? In particular, we'll ask the question, can we successfully predict the top 1% of queries? So if we want to identify the heaviest resource consumption queries. This is a precision recall graph. To interpret it, the x-axis shows the percentile of the predictions. So here, if we say 95, means the 95th percentile of the predictions. So that means this data point contains the top 5% of the predictions made by the model. Now, since we want to predict the top 1% of actual queries, the most interesting point to look at is the 99th percentile of the predictions. And here, a positive is if we successfully find a query or successfully predict that a query is part of this top 1%. Precision is true positives divided by the total number of predictions within that percentile. Recall is the true positives divided by the total number of positives that exist. So if we look at the 99th percentile, we get a precision in recall figure of 0.77. This means that 77% of the top percentile of predictions are within the top percent of actual slow or heavy resource consumption queries, which is not too bad. It's 3 out of 4. It's not. It could definitely be better, but it's this is something that could really make a difference. Unfortunately, this conference came maybe 2 weeks before we managed to get this into production. We're close, but not quite there. But these results would indicate that we should be able to identify a lot of the heavy queries and filter them out or redirect them to the lower priority zone. So I'm hopeful that we'll see some good results here. But it's a work in progress. There's a lot more we could do, a lot of new features we could add. The network topology, these results are based on a neural network with a single hidden layer. The only experiments we've done have compared that to a pure linear model, and the neural network gave the best results. So we could do a lot more experiments to see with network topology to see what results we could get. There's also other techniques that could be explored further when it comes to dealing with noisy data. A couple that we've dabbled a little bit with are one called random sample consensus. This is an interesting approach where you take random samples of your data and fit a model to a random sample, and then see which data points consistently fail to fit into any of these models that you've created. And if you have data points that never fit or very rarely fit into these small data models, then they're probably outliers. And then you can just throw away those data points and then refit on the inliers instead. But it's fairly resource intensive, and so far we haven't seen any good results. But it's something that is useful for dealing with noisy data. Ensemble methods are also something that have been well known to work with noisy data. And it's ensemble methods, you combine multiple models together in different ways. And since different models might be better in different ways for dealing with noisy data, often when you combine them together, you might the sum of the parts is greater, or the whole is greater than the sum of the parts. And this is something we've also dabbled a little bit with. Also haven't got great results yet, but I'd be hopeful this could also improve the results once we work with it a bit more. As I mentioned at the start, this is just one project in a larger track where we're looking at ways to improve our services using machine learning. Just 2 weeks ago, there was a conference in Grenoble in France, the European Conference on Information Retrieval. There was 2 tracks on deep learning. There was a track on classification and learning. There was a track on recommendations. Almost 40% of the papers at this information retrieval conference were directly related to machine learning. So there's a large intersection between machine learning and information retrieval. And this is something that we feel we need to be part of. And we have 35 billion documents, and we have millions of queries every day. So we have the data to be able to perform some interesting things. Just some examples of some other ideas we've been playing with is improving the relevance of the research results that we give back to our customers. So if there's a long list of documents returned, we want to order them in a way that a user sees the most relevant documents at the top of the list, and using user interactions to be able to tailor this personally for each user. Something that was a topic of a recent internal hackathon was text generation. We have several use cases where our customers need to be able to see the ingress or the summary of a document. With many documents don't have an ingress or summary, but what if we could generate these? Advances in deep learning have meant that text generation is becoming much more powerful over the past few years. And this is something that we think could be really useful to do. Deep narration is trying to generate text describing a set of documents and how it's different than a background set of documents. It also could be a different way of presenting information to the users. Today we also only provide search results, but we could augment that with recommendations based on the searches we see and what results we give back. We could also provide recommendations of what we think the user might be interested in. And we could expand queries. So users don't always know exactly what they need to look for, but based on our knowledge of the words within the documents we have and our knowledge of the queries that other users have been using, we could potentially expand those queries in a smart way to get the user what they want. That was the last technical slide. I want to thank the rest of the people in Meltwater and Gothenburg for their feedback for this presentation, particularly Team Horace, and more specifically Johan Nielsen Hansen, who was a big contributor to this work, and Mikkel Johansson, our team product owner and engineering manager, who was the inspiration behind the work. Thank you.